All right, just for the video, there's some stuff missing here. Oxidation, the oxidation half reaction. Over here, and then the Zn2 plus should be 1 molar. Over here we got copper 2 plus 1 molar. This, the most convenient thing to use is copper. Plating copper on copper is fine. And so the most sensible cathode to use is copper metal, but it need not be. And at the cathode, what happens? Reduction. And so what's the reduction half reaction here? Cu2 plus 2 electrons yields Cu solid. Now, in batteries, we like to label one electrode positive and another electrode negative. And so which one of these electrodes is positive, which one is negative? Anode is negative, cathode is positive. Good. And this battery won't operate unless we have a salt bridge, because the salt bridge does what? What's the purpose of the salt bridge? For charge balance, right? So we neutralize space charge, or we maintain charge balance with the salt bridge. And so this salt bridge is not showing me which way the ions go. So the potassium ions, which way do those go? To the right, to the cathode. Cations migrate to the cathode. And the nitrate ions migrate to the anode. Anions migrate to the anode. So we just got to show the potassium is going this way, and the nitrate's going this way, and then we show the net reaction. And we should show E naught of the cell is equal to the anode potential plus the cathode potential, which is missing here. The anode potential is, I had it written down earlier, and the cathode potential is 0.34 volts. I think this is plus 0.763 volts. The anode potential was plus 0.763. The cathode potential was plus 0.34, and they gave us a cell potential of 1.103 volts. Okay, that would be a complete diagram for that. Okay, let me just talk a little bit about this here. Electrical work, we can calculate. Electrical work, you know, how much work is it to push electrons through a circuit? Well, it's going to involve work. The amount of work that it's involved depends on Z. Z is the moles of electrons transferred in the balanced redox reaction. So Z is the moles of electrons. So some people call this N rather than Z, because N is a symbol we typically use for moles. F is this guy's constant, Faraday's constant. F stands for, or is this. Okay, here. 96,485 coulombs of charge per mole of electrons. And so it's, if you have a mole of electrons, how much electrical charge is there? That's 96,485 coulombs. E is just the cell potential. Oh, there it is. When products are in their standard state, what is it saying there? When products are in their standard state. Oh. Well, you know, the driving force we can convert into electrical work. The driving force for this reaction is going to be converted into this. And so this is the maximum amount of work we can do, is if we can just push the electrons through and drive the electrons through the external circuit. And so it turns out that delta G naught, when we're under standard conditions, is equal to ZFE naught of the cell. And so it depends on how much force, electromotive force, we're pushing on those electrons there. And so this is the equation that we have here. Delta G naught is equal to Z minus ZF E naught of the cell. And so our relationship between delta G naught minus ZF E naught of the cell. And therefore, if we know E naught of the cell, we can calculate delta G naught, because this is moles of electrons. And so the units here would be moles, and the units here is coulombs per mole, and E is volts. Do you know what a coulomb times a volt is? A coulomb times a volt is a joule. And so this gives us how many joules of energy. Something funny about cell potentials. These are reduction potentials here. And so we want the reduction potential. Iron 3 plus 3 electrons goes to iron solid. This is not on our chart. What's on our chart is iron 2 plus 2 electrons goes to iron, and iron 3 goes to iron 2. So if we can combine these two, then we have this one. And so this is like Hess's law. Hess's law is add up these two equations, we get this net one. But the funny thing about E's of the cell is this. E naught of the cell, these are not additive in the sense. We can't just add these together. It's weird, but we can't add those together. I have a good analogy for that, though. Slips my mind. We'll come back in a moment. But we can add the delta G's, energies. And so these are like intensive properties. These are extensive. These depend on the amount. Energies always do. And so the energies we can add. Once we add those together, we can get delta G naught. And then from our delta G naught, we can calculate our...
Did you say energy is intensive or extensive?
Energy is extensive.
And that allows us to add it.
That allows us to add it like that. Right. The reason is this. Let me show you why the cell voltages are intensive. If I have 1 gallon of 1 molar Cu2+, hey, you know that's going to have some kind of reduction potential, right? In fact, I know the reduction potential. The reduction potential is plus 0.34 volts. Plus 3.34 volts. Now, I'm going to go with this. I'm going to go with 2 gallons. If I have 2 gallons of 1 molar copper 2+, does that double my voltage?
No.
Is it all of a sudden, is it going to be E naught is going to equal plus 0.68 volts? No. No, it's going to be, surprisingly, it's going to be plus 0.34 volts. Why? Because it's the same concentration. The same concentration. But in terms of energy, let me tell you this. If I have a gallon of gasoline, I don't have much time, but versus 2 gallons of gasoline, is 2 gallons of gasoline twice as concentrated? No. But will it have twice the energy?
Yes.
Yes. And so this is the same thing. 2 gallons is not twice as concentrated, but it's going to have twice the energy. So this is why energy is extensive. Cell potentials are intensive because cell potentials depend on the concentration, pressure, and temperature. All right, I got to stop here because we're out of time. We'll finish up. I'm going to kind of whiz through chapter 20. That's why I decided to do PowerPoints. I'm going to try to go through chapter 20 quickly. And it's not because we're going to test on it soon. And it's not because